July 1st, 2025. In the quiet pre-dawn hours over Chile, the Atlas Survey Telescope picked up a faint moving point of light. Within hours, observatories across the world were alerted a new object was entering the solar system, moving at a blistering 130,000 miles per hour. At first, astronomers assumed it was just another long-period comet falling in from the distant Oort cloud, but the early orbital data told a different story, one that made every astrophysicist stop and stare. This wasn't just another icy wanderer. Its orbit was hyperbolic, with an eccentricity of nearly 6, far beyond the limits of anything gravitationally bound to our sun. Most comets trace stretched ellipses, looping around the sun before heading back out again. But not this one. Its trajectory meant it wasn't coming back. It was a visitor from another star system, an interstellar nomad making a one-time pass through our cosmic neighborhood, before disappearing into the darkness forever. Soon, the object received its official designation, 3I ADLAS. The prefix 3I marks it as the third confirmed interstellar object ever detected, following Oumuamua 1I in 2017 and 2I Borisov in 2019. But 3I Atlas was different, astonishingly different. Early photometric readings hinted that this thing was massive, perhaps up to 15 kilometers across. To put that in perspective, it was hundreds of times the surface area of Borisov, and thousands of times larger than Oumuamua, which was no bigger than a city block. Even the most conservative estimates placed Atlas in the multi-kilometer range, solidly among the largest cometary nuclei ever recorded. Size matters in the cold mechanics of space. A nucleus this big should act like a thermal sponge, slow to heat, slow to react, sluggish to show any activity until it gets close to the sun. Yet as astronomers ran their models, something didn't fit. Its brightness and coma size, the glowing halo of gas and dust that surrounds an active comet, were far too large. For the distance it was still at dot by calculating the reflected sunlight albedo and observed magnitude. Scientists realized that 3I Atlas was wrapped in a colossal cloud of material, stretching tens of thousands of kilometers across, like a red ghost blooming in the cold void. It was already active, venting gas and dust into space, even though it was still far beyond Jupiter's orbit, where sunlight is barely more than a dim shimmer. At this distance, around 6 point for astronomical units from the sun, the temperature is brutally low, roughly -200 C for most comets. That's a dead zone. Water ice, the standard fill for cometary jets, stays rock solid until around 3 astronomical units. No comet should be spewing vapor this far out. Yet 3I Atlas was alive, glowing brighter with each passing week. Calculations stunned the community. Over 10% of its surface was already venting material, a level of activity almost unheard of, even for the most energetic comets much closer to the sun. Most comets only exhibit 1 to 3% active surface area, and only after they've thawed near Mars or Earth. Something was driving ATLAS that wasn't water. What was fueling these premature outbursts? Could it be exotic gases, carbon monoxide, methane, or carbon dioxide, that vaporize at far lower temperatures? Or was this structure somehow porous or fractured, leaking trapped gases from deep within? The mystery deepened when the James Webb Space Telescope JWST locked onto the comet, with its near-spec spectrometer, designed to read the molecular fingerprints in reflected light. The results hit like a shockwave across the scientific community. The data showed that 3I ATLAS's coma, the gas cloud surrounding it, was 99% carbon dioxide, not water, not ammonia, not methane, almost entirely CO. The outgassing rates were precise and staggering. Carbon dioxide, 129 kilograms per second. Water vapor, just 6.6 kilograms per second. That's a ratio of 8 to 1, 8 times more CO than how. No known comet in our solar system even comes close. The average ratio for long-period comets is typically the opposite. Water dominates, with only trace amounts of carbon dioxide. This flipped the rulebook upside down. In percentage terms, nearly 90% of the gas escaping from 3I Atlas was pure carbon dioxide, with water making up less than 10%. Even the rare CO-rich comets in our system, like 6-7P Churyumov-Gerasimenko, studied by Rosetta, pale in comparison. And there was another clue hidden in the light. JWST spectra showed the presence of tholins, Complex organic compounds formed when ultraviolet radiation bombarded simple ices over millions of years. Tholins are what give Titan, Pluto, and some comets their reddish hues, but on 3I ADLAS, the signal was intense, a deep red signature unlike anything seen in typical solar system comets. It suggested a surface that had been exposed to interstellar radiation for eons. Far beyond the protective reach of any star, this was no ordinary visitor. It was a fossil from another star system, its chemistry shaped by alien sunlight and cosmic rays across untold light years. The laws of comet chemistry, once thought universal, had just been broken, and astronomers were only beginning to understand what that meant. The initial results from the James Webb Space Telescope had shaken the astronomy world, but science demands repetition, so the team led by Dr. Michael S.P. Kelly and his collaborators ran a series of follow-up observations, each one probing the spectral signature of 3I Atlas with greater precision. The outcome was undeniable. Each observation returned the same inverted pattern. Carbon dioxide dominated everything. Water barely registered. Trace hints of carbon monoxide and carbonyl sulfide appeared, but none came close to matching the runaway CO output. The spectral lines were crisp, unmistakable, and consistent across multiple instruments. There was no room for calibration errors or misinterpretation. Whatever 3I Atlas was, it wasn't a normal comet in any sense known to science. For the first time, astronomers were staring at a molecular fingerprint never before cataloged, a chemistry so extreme it forced the entire field of cometary science to rethink what was possible when an object came from beyond the sun's domain, a comet that defies the sun to understand 3I ADLAS. Researchers turned to physics. Most comets remain inert until they fall within about 3 astronomical units of the sun, roughly the orbit of the asteroid belt, where solar energy is finally strong enough to vaporize water ice, the main driver of cometary activity. But Atlas began venting violently while still beyond Jupiter's orbit, where sunlight is 25 times weaker and temperatures plunged below -220 C. The explanation lay in its unusual chemistry. Carbon dioxide ice, unlike water, can sublime it, transform directly from solid to gas at temperatures as low as 20 to 30 Kelvin, the 50C to -240 Celsius. That means even the faint warmth of sunlight at 6 astronomical units was enough to set CO free. This wasn't just a big frozen rock, it was a porous world, riddled with pockets of trapped gas. Models now suggest that the nucleus of 3I ADLAS, roughly 15 kilometers wide, resembles a cosmic Swiss cheese, a fragile lattice of dust, rock, and volatile acids dot as sunlight seeps just millimeters into the surface. Carbon dioxide trapped in voids begins to boil off, building up pressure beneath the crust. Eventually, that pressure bursts through weak spots, sending jets of gas erupting into space at hundreds of meters per second. These outbursts carry dust, ice, and debris, creating the vast glowing coma seen by telescopes. The physics is stunningly efficient. Even a tiny temperature rise, just a few degrees, can trigger a chain reaction, venting enormous amounts of gas. Thermal models show that over 20% of 3I ADLAS's surface is now actively spewing material, an extraordinary fraction for a body of its size. For comparison, Earth's most active comets rarely exceed 5%. What keeps this activity going is not just sunlight, but the comet's structure, high porosity, low thermal inertia, and a composition rich in hypervolatiles like carbon dioxide. It is, in every sense, a comet built for cold, one that can roar to life where others sleep. An origin beyond the familiar Earthly chemistry offers a crucial clue to its birthplace. Comets like this don't form in star systems like ours dot in our solar system's protoplanetary disk. Water ice dominates the outer regions. Carbon dioxide and other volatiles freeze out farther away, beyond what's called the CO snow line. But if 3I Atlas formed in a region with less oxygen and fewer heavy elements, such as the thick disk of the Milky Way, populated by ancient, metal-poor stars, the balance shifts dramatically dot in such environments. Carbon-based ices can become the primary condensates, while water remains scarce. The result? Bodies rich in CO and other hypervolatiles born in alien conditions. Isotopic hints from Webb's data seem to back this up. The ratios of carbon and oxygen isotopes differ slightly from those typical of our solar system, suggesting that 3I Atlas may have condensed from a disk with a completely different chemical recipe. A world where carbon was king and water was rare. If true, this object is a time capsule from a planetary nursery that predates our sun, a message from a part of the galaxy forged under entirely different rules. The controversy, natural or artificial, but not everyone sees 3I Atlas as purely natural. Among those watching closely is Dr. Avi Loeb, the Harvard astrophysicist famous for his bold speculation that one eye, Oumuamua, might have been an artificial probe. To Loeb, 3I ADLAS presents an even stronger case for deeper scrutiny. The object's orbit is unusual, nearly retrograde, at 175, slicing backward through the solar system's plane at an angle of only 5 off the ecliptic. Such geometry is rare for interstellar bodies, and Loeb notes that its trajectory almost seems too perfect, cutting through the planetary plane in a sequence that will take it past Jupiter and near Mars's orbit before vanishing once more into interstellar night. Even more puzzling are its photometric wiggles, small, rhythmic variations in brightness that don't align with normal comet rotation models, and, of course, the chemistry that refuses to change. If this is a natural comet, Loeb asks, why does it behave like no other comet we've ever seen? Why is its coma almost pure carbon dioxide, with water nearly absent? To him, these questions open the door, however slightly, to extraordinary possibilities. Could 3I Atlas be more than frozen rock? Could its jets, its chemistry, even its orbit be signs of artificial design? Most scientists remain cautious. The majority see natural explanations as more likely, the product of exotic chemistry rather than alien engineering. But even they agree, 3I ADLAS is a once-in-a-generation anomaly, a visitor that stretches the boundaries of every known comet model. Countdown to Perihelion. Comet's closest approach to the Sun, Perihelion, is set for October 29, 2025. As it swings behind the Sun from Earth's perspective, telescopes across the planet and in orbit will track it relentlessly, searching for one crucial clue: a surge in water vapor. If the heat of Perihelion finally wakes the water ice buried deep inside, then standard models will hold, and 3I ADLAS will be a strange, but natural, interstellar relic. But if water stays low, if the coma remains dominated by carbon dioxide even at peak solar heating, then the mystery deepens, and the case for something truly new, or truly alien, becomes impossible to ignore. Until that day, 3I ADLAS stands as proof that our solar system is not the standard, but an exception in a far greater cosmic diversity than we ever imagined. Each passing day it grows fainter, stranger, and more beautiful, a messenger from another sun, whispering secrets from a chemistry our world has never known.